کلا مطابق فکر کنم رفتن
یه ساعتی دیگه من ذهنم آلمانی بود.
احساس
یه وقتش قهوه بود. به منم گفتن بیا بریم قهوه قبل از چیزی گفتم الان میگم.
با بیکر در زن.
Hello.
Hi. So let's close this curtain as well. Have a شرف خیلی something is working. The guys haven't come yet.
No, they are still outside.
Yeah.
Has this new
Coffee
project
before the
invested?
seminar, coffee after seminar.
Well, it's right sometimes, yeah.
Antonio, do we know if it lasts longer?
Okay, it's bigger, it's brighter.
But do we know
And
how it
colder.
handles the heat?
Okay, so
Okay. It's switched on automatically from time to time. On Monday it was on, and today it was on as well. And then I was playing with the options, and it seems that it was configured that after electrical shutdown, when you plug it again, it will start automatically. So I interpret that was I changed that. Let's see. But if you pass by and you see that the memory is on, please turn it off.
Elham Saremi, so Elham Saremi, so Cardenas is the research director at CEPCA, and Elham is visiting this week.
Okay.
Yeah. Yeah. So this is really interesting research. So we've been working on this in the last 2 years.
Okay.
Elham and Natural Turkey. Yeah. So now Elham will talk the rest.
Yeah. No spoilers.
Yeah, exactly.
So you are here all the week?
Yes.
Okay. Okay. That's a moment.
Yes.
Nice.
Okay.
Okay. Okay, well, let's start. Thank you very much for being here. It's a pleasure to present the new beamer. Let's hope it doesn't get into overheating for being turned off all the night probably. So today we have Elham. She did the degree in the physics astronomy degree in Tehran, and then also the first postdoc in the IPM. And after that, she moved to the IC, where she's actually doing her second postdoc. And today she's going to talk us about laws of brightness with Euclid. So, all yours.
Hello, everyone again. It's my pleasure to introduce my work in the CEPCA. My talk is about a study of low surface brightness structure in the near IR. In the near IR, due to higher background and more variable background than optical, and from stronger atmospheric absorption and telluric emission in this wavelength, a study of extended faint object will be difficult, okay? And also IR detectors more complicated than optical CCDs. However, if we learn about the faint extended object, the study in the near IR are valuable and unique. So we start this work. First of all, let me introduce our team. Yes, Ignacio Trujillo and Johan Kanapan, Zohra Ghaffari and I, working at the IAC, and Mohammed, do you know, at the SEPCA, yeah. Here I am talking about data we have used. LSSD and Euclid in this decade will map 10,000 of square degrees with an overlap area around 9,000 square degree. Euclid, in addition to wide survey that cover around 15,000 square degrees, have three deep fields. One of the field of Euclid is Euclid Deep Field South. Euclid Deep Field South covers around 23 degrees of sky near to the ecliptic pole. With this area is with the low galactic extinction and low stellar density, so it is it has high potential for discovery, a new exciting discovery. Okay, and the good point is LSSD also will observe this area in as a fifth deep drilling field of in the Euclid deep field, all of Euclid deep field are 2 magnitude deeper than wide survey, and also about the LSSD is deeper than wide fast survey of LSSD. Euclid will observe this area, Euclid deep field south, in the Y, J, and H filters, and Y, J, and H filter, and LSSD will observe in the optical, and this field it continues viewing zone of JWST, W first, and ALMA. In 2020, Spitzer observed this area in mid-IR, and you can see the wide wavelength gap between the Spitzer filters and Euclid filters. A K-band survey can cover this gap. A K-band can provide a comprehensive picture of galaxies population in early universe, and the K-band can help us to discover the galaxies in redshift higher than 2 and more, while in the other wavelengths it's possible due to evolved star and dust, significant amount of dust, we can't see very good this redshift, this galaxy. So the K-band is very important. The VISTA telescope, the Visible and Infrared Survey Telescope for Astronomy, VISTA, as a ESO's parallel observatory, is the largest survey telescope in the universe, and VISTA works at the near IR. VISTA, in the first 5 years of operation, observe all of the most southern hemisphere with the 6 surveys, such as VHS, Viking, and so on, with different depths. Okay, And in the second cycle of surveys, VISTA continued the works in some surveys such as whales, sharks, and Euclid deep field south, or in the K-band or KDFS. The camera of VISTA, that named VIRCAM, in this camera, as you see, has 16 independent IR detectors with a large gap between the detectors. Okay, these gaps it's due to the technical constraints, and for having a full field of view around 1 cross 1.5 square degree, we need to at least 6 offset footprint to fill out the full field of view. Yes. And now I will speak about the why did we need to develop a software for VISTA? Because VISTA many years is working, and VIRCAM is working, and it has some standard pipeline. Yeah. This question is important. Why we need to develop a new software? Very soon we realized none of the standard pipeline for VIRCAM were suitable for the study of low surface brightness structures. For example, you can see the one example galaxy, spiral galaxy, NGC 4030 in the optical. This is the SDSS image. And now you can see the reduction of this image in the K-band with one standard pipeline of VIRCAM. Okay? You can see how the standard pipeline destroys the outer skirts of the galaxy. This is K-band, while it can be imagined this is UV. There isn't any diffusion, okay? And this is very amazing. This is not a real figure, because in the K-band we expect even less massive star can be seen, okay? And this is all of the outer skirts of galaxy is destroyed. So we decided here exact where we decided to write a new pipeline for this project. Our pipeline, that name is Nasim. Nasim is a Persian word that means breeze in English, a breeze. Our pipeline is full automated, is a full automated process for preserving the low surface brightness structures in the near IR. And our pipeline written in the managed workflow. I speak about this. Okay. Now, first let me show the result of this pipeline. Okay. You can see the comparison between the reduction of NGC 4030 galaxy with the standard pipeline and with the Nasim pipeline. The difference is quite obvious, no? Especially in the preserving the outer skirts of the galaxy, the difference is very quick.
Which filter is this?
Yes.
Which filter is this?
Which filter? K-band. Yeah. I speak in the K-band to end of my speak. The pipeline now it's in the K-band, but it's suitable for all of near IR, other filters for VIRCAM. Okay, Y, J, H, and K. Now I speak about the how did we the access to such great result. Yeah. Yes, we use the Gnuastro. Gnuastro, as you know, is a package of GNU. Is a unofficial package of GNU with consisting of many programs and libraries for the manipulation and analysis of astronomical data. With Gnuastro, we could remove the flat patterns and all of the larger scale signature instrument signature of the complicated IR detectors of VIRCAM, and also we could use the non-aggressive sky removal for this pipeline with Gnuastro. Our pipeline designed in 3 phases. In first phase, we prepare the data from the ESOS archive, okay, the raw data, and after the validating the data with SHA, we start the preparation phase. In the preparation phase, we downloading the data, create the metadata and categorizing of images, and in the main phase, we read. The main phase is 3 phases in the main phase, and we redact the image in the many steps. All of steps is automatic. You can see example of raw exposure of VIRCAM for this survey. And you can see the, how the signature of the IR detectors is very different and also very unstable, yeah, during the time. There is a NGC galaxy here in this raw image. Can you find it? Yes. Because of the high background?
The
You
blue
see?
one? Blue.
No.
You have an idea?
Yes, the top of the third one.
Top of the blue? Here?
Yeah, no, top of that.
The image of the image of
The number of detectors is 1, 2, 3, 4, 5. Which
Seven, I
detector?
think in 7.
7 detectors. And these?
Yes. Maybe.
Yeah.
Maybe 15. Is that point
Maybe
there?
15.
Yeah, it's the core
white,
of the galaxy.
the white thing in the second last. Yeah, this.
This is the fault effect of the detectors.
Look, it's surprising. You don't even see the stars, not just the galaxy. You don't even see bright stars. Yeah.
Not anything.
This is more like normal in the cave.
Now I have a simple flow chart for main phase of the pipeline. Okay. You can, in the right of the slides, you can see the name of the Gnuastro programs for each step. Some of the Gnuastro programs, because all of them use in all of the steps. Yeah. You can see the dark remove images for one exposure, the 16 detectors in one exposure. Dark remove only, removing the dark only can clean the image for 1%. Okay, and now you can see the all of dark removing exposures in one night, 42 in one night. In the KDFS survey, we have 15 types, and each type have 20 nights observation, and each night have 42 exposures. Okay, and this is the only for the detector 7. Okay, only for one detector for all of the exposures. And the main step of the pipeline, flat fielding. For flat fielding, we don't use dome flat or twilight flat. Yeah, we use the science images for creating the master flat. We create master. We apply the flat fielding in two stages, in two steps. In the one step, in the first step, we create the master flat from all of exposures in one night. Yeah. And after applying two images, you can see the one exposure, and you can see the objects appear little by little. But with the strong program of Gnuastro, noise chisel, we enable to mask the objects in this step. Okay, we mask the objects in the flat corrected images and dark removed images as well. And after that, we try to repeat the flat correction for iteration 2. In the second iteration, we had many challenges to select the method for best method. I try to speak about this later. But now only I say this in this step we create master flats as many as the exposures, and after they apply this master flat in the image, now you can see the NGC in one detector. Okay. For sky removing, we, as I said, we use the non-aggressive method, and we try to use only a constant value for sky removing to don't lose anything. And for photometric calibration, we use the many Gnuastro programs for this. For example, we use the two-mass data, two-mass catalog for this, and we try to create a catalog in the images for the, and matching the catalogs with the two-mass catalog. And after that, we found the 0 points for each image. We had many limitations with the two-mass, because the two-mass is not complete in more than 16 magnitude in the AB system. And finally, we have a very good photometric calibration. In the next step, astrometry, we use the solfid in the iteration 1 of astrometry for having the full control in the solfid program. We try to use the Gnuastro program for creating the catalog, and as a entrance of the solfid. And after that, in the second iteration for astrometry, we use the scan for the solving the distortion map. And resampling. In the resampling, for the first time, we use the very new program of Gnuastro, ASTWORD, board program, that name ASTWORD. Based on the board program, we could based on the mixing pixel technique, we could have very good resampling of images. And finally, you can see the final quad for NGC, galaxy, and weight map or exposure map of that. I come back to this final image. Yeah. And how did we could how did we can manage 10,000 of images in this pipeline? Okay, bit manage. Manage, as you know, is proper for a reproducible project. Manage help us to have a pipeline independent of the host operating system, with full of programs and libraries, from downloading the necessary library and programs, from downloading the data to creating final code. Okay. Manage can enable us to be independent from the C compiler of the operating system to high-level programs such as ls, cp, and bash commands and everything. Using the GNU make in the manage, we could have high speed and modular and clean architecture for all of codes. About the speed of this pipeline, all of the steps from the creating the data from source archive, the downloading, and all of the steps to until creating the final code for each image only takes less than 4 seconds. It's very interesting. And also, the good point about this pipeline is about the decreasing the required needed capacity for the processing of images. Okay, I can decrease 2.85 gigabytes for each image capacity needed for the processing of image. For total of this survey, we could save the 755 terabytes. It's very good for the big data. Yeah, and now I try to speak about some of the steps and some more challenging steps of this pipeline. For example, flat building. In the flat building, we experienced many methods and many techniques in some months. Yeah. In the first method, we used all of images in one night for creating the master flat in 2 iterations. Okay, and you can see the background is not very good. And we try to another method. In this method, we create the master flat for each 10 or 11 continuous image in each night. I said each night has 42 images, okay? 42 images observed in only 1 hour, only 1 hour. We separated 42 images to 10 and 11 images for creating the master flat in iteration 2. And you can see the result is very better. Here in the top of the slide, you can see the master flat in iteration 1 and 4 master flat in iteration 2. And very nice point is the ratio of master flat 2 into master flat 1, okay? And you can see the very fast changing of sky luminosity in only 1 hour. Unfortunately, because due to the bad dithering or not proper dithering in the observed in this survey, we see the persistence. Sorry. We see the persistence effect. This effect is very famous for the big object, okay? And after that, we try to decrease this effect. Many challenge in this step. For example, we try to replace the values of pixels in the objects for the master flat 2 in master flat 1, and many methods we tested, but we don't believe this because the background was not good, very good.
Excuse me, why it's happened for just a large object? Doesn't happen for a small object? Why?
No, doesn't have doesn't see in the small object because this is the effect result of the dithering. Okay, in dithering, as I said, we have around 6 or 7 offset power print. Okay, for fill out the full up fill up of your VIRCAM. Okay, so we don't have a proper dithering, yeah, in the changing the in the moving of the big object. For the small object, yeah, this effect doesn't see because this effect is a result of collecting the image, yeah, and the effect of higher noise, yeah, higher noise than signal.
So for the small objects, it's easier because you reject the brightest pixel, right? When you collapse, when you do the master. But when you have a systematic that it's very close to the noise level, you don't reject those pixels easily when you average. So that's why extended flux structures may persist when you...
Let me explain better. For example, with when we create all of the images in one night for master flat, we didn't see this effect, okay? Because we have enough images for moving the objects, okay? But in this method, with using the only 10 or 11 image, yeah, we don't have the enough images for moving the big object, okay? So in the gathering of the images for creating the master flat, yeah, we in fact we increase the noise.
So just to phrase what Elham once said in another way, just to complement, the small objects, the dithering is sufficient to replace the bad pixels, the persistent pixels of the small objects, because they're small and the dithering is small.
Yes.
So the dithering can fix the small objects. But because this galaxy is much larger than the dithering steps, it can't fix the problem.
Thank you. It's better. Yeah.
That's an important thing, and it took us a long time. We're working on this for, I think, 2 or 3 months.
Yes, exactly.
Or even more. So yeah, this is it's a really complex problem in IR detectors generally.
Yes. And finally, we success to decrease this effect by a new technique, adaptive flat filling. Okay. In this technique, we use the 11 images for creating the master flat, but as many as the exposures, okay? And for the first time, we could decrease this effect. And one of the nice points in this pipeline is removing the wavy patterns in the image. Yeah, we could using the arithmetic program of Gnuastro and collapse mean option. After the masking the object and collapsing the one dimension lower. Okay, we could then remove the we could to have higher signal to noise, and then we could remove these patterns. You can see the wavy patterns here, and this is the after removing these wavy patterns. And then some example of results. For example, NGC 1494 galaxy, if you see, you saw at the flow chart, in the 2-mass survey, it's here. The 5 sigma limiting magnitude for this image, it's around 16 magnitude in the AB system, and you can see the one other survey of VISTA VHS for this galaxy, and this time VHS could have the 30 times brighter than 2-mass, and finally the result of nesting pipeline for this galaxy, we arrived to depths for the point source, depths of 23.3 magnitude in the AB system. And here there is the surface brightness profile. I drew this surface brightness profile based on the radial profile script of Gnuastro. And you can see this surface brightness profile for the 2-mass data. And now you can see the surface brightness profile for the VHS data. And the limit of magnitude for VHS is 25.1. And now our result for surface brightness profile of this galaxy. You can see truncation radius is very clear, and you can see this radius in this ellipse. We arrived to surface brightness limit around 27.7, equivalent to 30 in optical. And although we have deeper than VHS due to the more exposure time, but this is very clear in the VHS reduction with the standard pipeline. Based on the sky removing, bad sky removing, they lost the truncation in the deeper radius.
Or in another way, they created a false truncation. Yeah, because they over subtracted the sky.
Yes, exactly.
What is the exposure time for 2 months?
In VHS in the survey, VHS is around
2 months and
2 months. I'm not sure, but I think it's around 1 minute.
I don't know.
I'm not sure.
Because it's another telescope. I don't know what the size of 2 mass.
I'm not sure about 2 mass, but in the VHS, the minimum time is around 1 minute. Okay. In the KDFS, minimum time is around 2 hours.
So
And
2 hours exposure time.
yes,
For-
deep KDFS is a deep survey. We have in the exposure map. Yeah, you can see very different depths. Yeah, we can see very different depths for the of pixel of the image. Yeah, it's around 2 hours to 5 or 6 hours. In this column, we have around 6 hours.
Total, not,
Total.
okay.
Yes, total.
Not like one exposure, we're talking total time.
No, no. For final
That's why,
time.
that's why I tell you the
Like,
exposure time 2 hours.
I speak about
calculate
this
the
image.
vector in.
Absolutely, like,
1 second.
Yeah, I
Something,
speak
some
about this
seconds.
image. This image is final quadring.
okay.
And total exposure
Okay,
is
total,
around,
right.
the minimum of total exposure is around 2 hours. Okay, and very nice result about the galaxy cluster. You can see one example of galaxy cluster in the J band from the VIRCAM survey. And in the J band, we don't see any nice intercluster lights, but in the I band, you can see some intercluster lights, ICL. And as we expected, in the peak of spectral energy distribution, SED, is for stellar population is around 1 micron, and we expect see the ICL in the around I band to the J band, but in this redshift, 0.7, this peak shift to the K band. And you can see very nice ICL here. And with the noise chisel and segment program of Gnuastro, we could detect and segment some many objects in this cluster, and you can see the black region is detection of the total of ICL. Very more of this eye, and this is show this pipeline is unique for high redshift studies in addition to local galaxy. About the documentation, all of steps in this work documented in the Git based on the managed workflow, and all of codes, all of issues, everything documented step by step in this pipeline. And after publishing the first paper, we can public.
We
we can publish the everything. And for the next months, we try to archive the images and catalogs, and also value-added catalogs for this survey. We try to archive to ISO archive KIDFS survey and Shark survey as well, and then we try to archive all of the VIRCAM data, for example, VHS and Viking and other surveys. You can see the how VHS survey in the green regions, how VHS surveys cover most of the southern hemisphere, and Viking as well for some of the parts of the this hemisphere. But I hope after the working JPass, we can hope to add Y, J, H, and KS filter to valuable filters of JPass, at least in the -5 declination to 5 declination. And enhancing these filters for the studying of multi-wavelength is very good. Also, we experience in the lights project. In the lights project, with similar technique in our pipeline, with using the Gnuastro programs and many similar, but only different about the IR detectors and flat fielding and background of the near IR. We experienced the study of low surface brightness in the optical, we arrived to depths of 31 magnitude per square arc second. Okay, in the optical with the similar techniques. Now I can see our experience in our team for in the optical and in the near IR is very proper to the ARCIS project, because in the KDFS survey, as a near IR survey and as a deep survey, we experienced and we faced with the many large area, and in the lights project we experienced only special targets. Okay, and all of them, I think this is very useful for the ARCIS. Thank you for your attention.
Yeah. Questions?
Maybe just one note for everyone else to follow. So the lights, just as an introduction, is using the LBT, the Large Binocular Telescope. So it's 2 8-meter telescopes that are in the optical, and so each one is R, one is G, and yeah, so they're optical, and it's
Yes.
the Large Binocular Telescope.
Yes. The total of exposure time for lights is around 130 minutes, 130 hours. Okay, but with low exposure time, we arrive to this depth.
This is the depth of LSST.
Did you apply the nesting pipeline for lights?
No, nesting pipeline is about the near IR, okay, and about the VIRCAM. But the techniques in the lights pipeline and nesting pipeline, because using the GNU program is very similar. But the difference is about the optical and near IR.
So does VIRCAM not take traditional flats, or you decided not to use them?
Yes, VIRCAM has a traditional flat, but it's not useful for the studying those sort of brightness. In the standard pipeline, as you can see, as you saw, we use the twilight flat. Okay, sorry. Yeah. Here you can see in the standard pipeline, the main difference between our pipeline and the standard pipeline is about two things: flat fielding and sky removal.
I would think that what you do better is the sky removal. I'm surprised that the fact that they kill the structure is because of flat fielding. It's more of sky structure, right? Because I wonder if you actually, okay, I'm coming from the optical,
Yeah.
but I do wonder if you actually correct the flat field of your detector, i.e. the difference in pixel sensitivity. Because I imagine that is a very small signal compared to your sky. You're clearly sky dominated, okay? It's K-band, absolutely. But I really wonder if you actually flat field your data. Using the definition of the optical, right? getting the pixel sensitivities. You clearly do a much better work at subtracting the sky. But do you actually flat field your data? Is the question.
Yes, as I said, the main difference is about the flat fielding and sky removing, okay? In addition to non-aggressive sky removing, that is that the effect of this is in the outer skirts is very clear. Yeah, the flat fielding also is important for this.
Yeah, so flat fielding, like what you showed when you only use 10 images to create the flat and the differences that it made. So it actually changes.
That's because you're sky dominating, right?
Yes.
The infrared sky is very variable. So if you use from the whole night, you basically lose that variability and you get the artifacts. When you contain it to 10 images, you kind of keep up with the variation of the sky and you get a cleaner sky subtraction.
No, this is for the flat. So this is to build the flat from the science images. Now, when you take the image from the twilight flat, the thing is that it changes the sky, even so the twilight sky also changes. That's the point.
Yeah.
So and using and on a large field of view, the gradient of the twilight flat becomes also important. Adds to that changing.
I'm just wondering if the actual, again, coming from the optical, for me, flat fielding is pixel sensitivity.
Yes. That's the goal here as well.
I just wonder if that signal, you can actually pick it up deep in the sky variation.
Yes, we do that in the optical as well with the lights survey. We've done exactly the same strategy to make the flats using the science images during the observation. And over there also, we saw the dependence on the compared to using twilight flats or using longer the whole night, for example, to build the flat. So in both cases, both in IR and in optical, we saw this effect. When you really want to push to the limit, that difference pops up. And then what happens with the standard pipeline is that difference, because it's a gradient, right? This dependency on the pixel sensitivity. So this gradient, because it gets poorly subtracted in twilight flats, for example, then it goes into the sky, and then it gets over subtracted during the sky with the standard pipeline.
Exactly.
But we don't want to over subtract that because we care about the very extended and very low signal to noise regions. So we don't want to subtract them from the sky. So we have to put a lot of energy on making a good flat. It's been in the last year, I think 70% of our time was on the flat, testing different scenarios.
Exactly. As Mohammed pointed this, I think in the standard pipeline, after the flat correction with twilight for that, they decrease the background with the sky removing.
Yeah, they over subtract the sky partly to fix the problems in flat fielding, because the problems in flat fielding then show up as a signal on the sky. And the good news is that thanks to JPass's observing strategy, we can do very good in JPass. Very good. We can build beautiful flats.
For dithering, yeah?
Yeah. The dithering is the best in the world.
Yeah. That dithering of VISTA,
we should really publish a paper on that.
Yeah.
For extended signal. Yeah.
I have a question regarding the intracluster light. So the intracluster light can be very useful to trace the dark matter distribution, and because you have the K-band, as you said, you can trace that and trace it for 0.7. Are you planning to collaborate? So is there a group in Euclid doing that? Are you collaborating with them on that?
Yes, the team of Nina Hatch in Nottingham. She's leading the ICL team, and yeah, we will be in touch. So as soon as Euclid starts to give the deep Euclid images, Elham is in fact going to the UK. So she got a postdoc in Southampton. And
Exactly in the EAS meeting in the last week, and yeah, we spoke about this and then collaborate with the ISL teams. Yeah,
Yeah.
about this, Miriam and other persons.
How many clusters do they expect to detect in the deep sea?
I don't know.
I don't know because now all of the survey doesn't produce, yeah, and
It's 20
I-
degrees, right? 20 degrees
20,
squared.
20
20 degrees squared. I didn't know they expected.
around 15 tiles, yeah. I reduced some tiles and I saw around 10 galaxy clusters. No. From the first image of the, sorry, this is hard.
Okay.
In the case of Euclid, so applying the same Nassim pipeline on Euclid near IR. That's one of the other goals as well. Once later, when enough Euclid data comes,
Yes,
we can apply the Nassim on Euclid data.
yes,
And
exactly. And this is the two other galaxy clusters. And we discovered the one faint object, yeah, maybe the dwarf galaxy in this type.
Oh, really?
Yeah.
Great. More questions? If not, we thank Elham. And thank you for coming. There should be an extra seminar on Friday. I'm still waiting for the alternative.
Thank you, Tom.
You're welcome.
Were there no questions on that?
I don't think so, because
There's another second. How is that possible? And you don't know?
It's the one by Rafael. Do you know?
Yeah, there is the Rafa.
Yes,
He was on holidays.